Welcome. Great to have you here. Why do capacitors look so radically different from one another? If they all just store electrical charge, why can't you replace a tiny ceramic disc with an electrolytic cylinder? The truth is, picking the wrong type of capacitor is one of the most common reasons custom circuit boards fail, oscillate, or straight up explode. Today, we are breaking down every major type of capacitor on the market. We'll look at their internal chemistry, their ideal use cases, and the exact physics behind why you need different dielectrics for different jobs. At the highest level, capacitors split into two categories: fixed, which have a set capacitance value, and variable, or trimmers, used for fine-tuning radio frequencies. Within fixed capacitors, you hit the most critical boundary line in circuit safety: polarized versus non-polarized. Polarized capacitors have strict positive and negative terminals. Connect them backwards, and the reverse voltage will rapidly boil the internal liquid electrolyte, leading to catastrophic gas venting or explosion. Non-polarized capacitors can be wired in any direction without risk. Let's talk about the workhorse of modern electronics, the ceramic capacitor. Specifically, multi-layer ceramic chip capacitors, or MLCCs. These are non-polarized, incredibly small, and boast exceptionally low equivalent series resistance, or ESR. But watch out for Class II ceramics like X7R. Under high DC bias voltage, their effective capacitance can drop by over 50%. For precision filters, always use Class I COG or NP0 ceramics, which remain completely stable across voltage and temperature shifts. When you need massive capacity in a small footprint, you switch to aluminum electrolytic capacitors. By using an etched foil soaked in a liquid electrolyte, they achieve enormous capacity, from 1 microfarad up to tens of thousands. However, their liquid nature is their downfall. They have high internal resistance, high leakage current, and they slowly dry out over years of operation, leading to classic power supply failures. Need absolute precision, zero distortion, and high voltage handling? Meet film capacitors. Utilizing plastic dielectrics like polypropylene, these are incredibly robust and have a unique self-healing property under voltage stress. This makes them the ultimate choice for AC mains filtering and high-end audio paths. For high reliability in dense spaces, engineers turn to tantalum capacitors. These are polarized solid-state components that offer massive volumetric efficiency without drying out like aluminum. But beware, they do not tolerate voltage spikes. Overvoltages can trigger a violent, self-sustaining exothermic reaction, meaning they catch fire. To get the best of both worlds, modern hardware uses functional polymer capacitors. By swapping liquid electrolyte for a solid conductive polymer, these achieve ultra-low ESR, handle massive ripple currents, and can comfortably run for decades without degradation. Finally, we reach the frontier of energy density: supercapacitors, or electric double-layer capacitors. They drop conventional insulating dielectrics entirely. Instead, they use an electrostatic double layer formed at the interface of activated carbon and an electrolyte. This allows them to bridge the gap between traditional capacitors and lithium batteries. While they can't match a battery's total capacity, they can charge and discharge millions of times at massive current rates without degradation, perfect for regenerative braking systems and memory backup power. Choosing a capacitor isn't just about matching the microfarads. You must balance voltage bias, ESR, temperature stability, and lifespan. Keep this guide handy for your next schematic design, and your hardware will stand the test of time.